So today we wrap up. You guys finally made it here. I think, yeah, there's something kind of fun about this ending with this particular lecture because what we can do now is actually tie together a whole bunch of different things that we've seen throughout this course. And in particular, I want to talk about variational autoencoders. And I sort of expect that I have a bunch of material on deep generative models that we probably won't have time to get to, but maybe we'll kind of skim through at the end. But in general, I think there's sort of great opportunity here to kind of see a lot of what's going on in deep learning from an inference perspective, from a probabilistic modeling perspective. And that's fundamentally what we're going to be trying to get at today. Okay, so reminders. Final exam is on Thursday, and the final poster session for 10/16, the submission deadline is December 10th, Tuesday, and then the presentations will be on December 11th. And we still have to finalize the exact time for the poster session, and we'll be sending that out on Piazza like tomorrow morning. So in my sleep-deprived state, I put together the final exam logistics slides here, so hopefully they're correct. So the actual exam itself is 2.5 hours long, so it's longer than our midterm exam was. And then we have Doherty Hall A302, which is down in the basement, if you haven't been there before. I think Akanksha and Karthika and Austin already mentioned on Monday that the material we're covering is only lectures 1 through 26. Like today's lecture, anything that we talk about today is not covered on the final exam. And then the format of the questions will look kind of similar to the midterm exam. And as usual, please bring a sheet of notes. I don't think we need that. So did you guys mention the sort of distribution of our content as well? Okay, so this is important to note. So 30% of the material is coming from before the midterm exam, but most of the material is coming from after the midterm exam. And so, so if we took the list of topics from before the midterm exam, you can imagine that sort of the way that we're writing our exam is we're taking all of these problems and we're kind of packing them all into one section of sort of a lot of short answer, multiple choice style questions. Just kind of the lighter weight questions. But at the same time, the reason that I always want to emphasize that we are covering sort of pre-midterm material is just that it's almost impossible for us to write questions about post-midterm material without referring back to the things that we've already done. So fundamentally, when you get the exam, you'll see that there's kind of a bunch of different sections, and those sections roughly correspond to the kind of big lecture topics that we saw and big homework topics that we saw in the second half of the course. And so, whereas in the first half of the course, we were kind of mostly thinking about ways of writing down models and representing conditional independence assumptions, and then how to do sort of the simplest possible learning, right? Settings where we have full observations and where we can do exact inference. In the second half of the course, we suddenly opened everything up and said, well, that's not always realistic. In practice, we usually can't do exact inference in the model that we actually want to write down. The model that we'll look at today, variational autoencoders, is no exception. And learning is in general going to kind of rely on more advanced techniques than just maximum likelihood estimation. It might involve things like variational EM, where we need to actually learn with partial supervision, or it might be things like structured perceptron or SVM, where we're actually sort of learning in the presence of map inference rather than marginal inference. And then we kind of looked at these three sort of big areas for approximate inference. One was that of map inference, and I think I actually kind of somewhat purposefully de-emphasized map inference as sort of a topic for approximate inference. We were mostly concerned with treating it as a mixed integer linear program where we could solve it exactly. But you also, on your homework, were thinking about this as an approximate inference method, where you were taking an LP relaxation of the ILP and solving that LP relaxation to get back an approximate solution to the inference problem. And then we also thought about specifically two MCMC methods, Gibbs sampling and Metropolis Hastings, and associated Monte Carlo methods, so that we can look at how approximate inference could be treated as a sampling problem. And then lastly, we looked at approximate inference from this optimization perspective and thought through how we could set up a mean field approximation and then treat the problem of optimizing KL divergence as the actual mode of doing inference. And then, so the online lecture, the one that was sort of my replacement for the Monday that I was out, was on Bayesian nonparametrics. And there we were thinking about how we could take this sort of standard setting where you sort of assume that you know how many or that you know a lot about the actual underlying distribution of the data. That you know, for example, how many clusters there are for a mixture model. And we sort of said, well, in fact, you could work in a setting where you don't know how many clusters you want a priori, and you let the model actually figure out that aspect of things for you, the actual underlying structure of the data. So today, the thing that's not covered on the final exam, we'll be talking about deep generative models. Okay, so I want to wrap up with just a word on variational EM so that we can, partly just to refresh your memory on this, and also to kind of paint a slightly broader perspective of what it was that we were doing with variational EM. So, so first I want to jump back to this unsupervised POS tagging example that we had used in order to look at an actual instance of variational EM. And so here, if you remember, our setup was where we have sentences only. And we further assumed that they were concatenated together into one long string. And the goal was actually to infer the part of speech tags for these unlabeled sentences. So those are, so the words were the W's here, the T's were the tags that we're trying to infer. And we assumed that we had a Bayesian hidden Markov model, which is one where we had parameters, phi e and phi t, and priors over those parameters, Dirichlet priors. And so we sort of decomposed this back into our usual variational notation as, alpha being the parameters of the distribution P, and Z being the parameters of, the actual hidden variables that we're trying to infer. And that included both the tags and the parameters of the HNM. And then X being the words that we actually observe. And so our mean field approximation said, well, we're going to decompose those completely so that all the variables are independent, conditioned on the variational parameters, theta. So, what I want to think about then is how can we come up with essentially variants of the framework that we looked at last time. And so to do that, so this table, there's actually, I think, a link to it, this high-level explanation of variational inference that I put on the webpage. So this table is sort of adapted from this example from Jason Eisner, which I think provides this really great picture of a lot of the different problems that we have solved in this course and that we want to solve. Okay, so before we jump into variational autoencoders, we're just going to establish some terminology in this example. So we're going to say that in this model, we have a couple different types of things that we're working with. We have the hyperparameters, beta. We have the phi parameters, the emission and transition phi parameters. And then we have the tag sequence, T. And what we're going to do here is construct a table thinking about different settings that we can look at for those three aspects of the model. And we can then articulate what optimization problem we're actually working with, and the name of the possibly approximate method that we're working with to solve the problem. Okay, so here's what I mean. So we have this big table here, and suppose in the first setting we are given the hyperparameters beta, and we're given the emission and transition parameters phi, and what you want to do is maximize over t. So here in this setting, the optimization problem that we're talking about is t equals an argmax over possible t's. This is like a vector t of the posterior p of t given the parameters phi and hyperparameters beta. Okay, so what optimization problem are we actually solving? I mean, I wrote down the math, but in words, what optimization problem are we solving if we're given beta and phi, and we're just trying to optimize over the t's for a given x? So you can assume that x is always given here. This is a lovely sort of exam style question, by the way, where we're kind of asking you to fill in the blanks here around what it is that how can you actually map this math back to sort of the terminology that we've used throughout the semester. So is this learning? Is it marginal inference? Something else? Yeah, it's just map inference, right? So why don't we make it, we call it map inference, or maybe map decoding, same thing. Okay, and if we wanted to actually solve this, we would need an algorithm to do it. And so, you know, an example of an algorithm would be max product belief propagation. Okay, or greedy search. That could be an approximate way. And max product BP is also called the Viterbi algorithm when we're talking about it for an HMM. Okay, so that's the first setting. So here, let's think about the second setting. Suppose now you are given the hyperparameters and the parameters, and you're trying to sum over t. So we could write this as an optimization problem where we're saying we want a distribution P of W given phi and beta, which is a sum over T of the joint P of W and T given phi and beta. And how would we describe what optimization problem we're solving here in words? Or if you'd prefer, you could suggest a method that could solve this for you.
Then we could do sampling and for different teams and then get a distribution.
Yeah, we could do sampling. We could do let's start writing some of these down. We could do sampling. Actually, let me be a little. I'm actually gonna, just so that the table ends up being really highlighting the point that I want to make. I'm gonna put some ideas over here. So sampling. We could do sum product BP. Right. So what is the actual problem that we're solving? Yeah, this is just marginal inference. And so I guess the one that I want to highlight here is that we could say that here we're doing possibly variational inference. Okay, so why do I say that variational is in parentheses here? Well, if we make the mean field approximation shown above, then you would be doing variational inference. Okay. As it turns out though, if you're given beta and phi, you can actually do exact inference by, say, sum product BP. Okay, so we don't have to turn to the approximate method, but it's useful to see that if we did use that particular mean field approximation, this would be an example of mean field variational inference. Okay, so let's keep moving. So next, suppose we wanted to say, for our third option, that we're given beta, and then we're going to maximize over the phi and sum over the t's. So in that case, we're looking at an estimation of phi as the argmax over phi's of, say, p of w given phi, right, which is implicitly summing out the t's here, times, say, p of phi given beta. Okay. So what problem are we solving here? You're given the hyperparameters, you're marginalizing out t, and you're maximizing over the parameters. So EM is a method, so we could say the method we're using is EM, and if we used that same variational approximation, it would actually be variational EM. But what is the actual problem that we're solving here? Is it maximum likelihood estimation? Well, if we cover this up, then we have maximum likelihood estimation. But we have this extra term, p of phi given beta. So what is this? This would be map estimation, because we have a prior over the parameters. Okay. And again, it's only variational in this case if we're making that mean field approximation. Okay, so now, in the fourth case here, suppose we're given beta, and then we sum over phi and t. Okay. So in this case, what you could think of this as doing is we're essentially estimating p of phi given w and alpha, and p of t given w and alpha. And this is really just the sort of Bayesian posterior inference problem. Right? We're trying to get a posterior distribution over the parameters or over the tags. And one way that we could do this, now looking back up at our example, is following what we were talking about last time, which is just say that is our joint distribution, p alpha of x and z, and this is our mean field approximation, and we're going to estimate, we're going to get a mean field approximation of the distribution over z. And so this, we don't call variational EM,
because we're not optimizing over anything. This is called variational Bayes,
where we're truly coming up with a posterior distribution, over the parameters and any latent variables.
Okay, so the last one is sort of an interesting one. And here, suppose you wanted to maximize over beta and then sum over both the phi and the t. Well, now, this is sort of like saying we're trying to find the alpha, that is the arg max over alphas of p of alpha given w. And this is called not the Bayesian posterior inference, but empirical Bayes. Because what we're saying now is
we aren't actually willing to commit to a particular setting of the hyperparameters. We actually want to learn what the hyperparameters are.
And in this setting, we're actually back to variational EM. This is just another example of it. And so, but the key thing that you can see here is that what we're doing is essentially setting things up so that, in our example, we can actually drop these terms, these sort of variational terms in parentheses. If we drop the mean field approximation, and do exact inference instead. So,
we were in a setting, I set things up so that we were in a setting where we could actually do exact inference or exact EM. Once we get down here though, we're still doing variational EM because we're still using a variational approximation to marginalize over some latent variables. In this case, it was phi and t. In case 3, it was just t. And then we're maximizing over some other parameters. And so that gets us our E step and our M step for variational EM.
Okay, so now, armed with sort of all of these
Different terminologies, we can see that, sort of given any model, you can start to, pick out different parameters and say, I'm going to maximize over these and I'm going to sum over those. And depending on what you choose, you'll end up in a different paradigm. Maybe variational Bayes, maybe variational EM, maybe variational inference. And depending on whether or not you're making an approximation, you need or don't need to use the term variation.
Okay, so let's look at a
Couple short examples here. So for unsupervised part of speech tagging, someone actually went out and tried this Bayesian HMM that we just talked about. And so the task is unsupervised POS tagging. The data is 1 million words of unlabeled sentences from the Wall Street Journal. And they sort of cheat because they have this dictionary that defines the legal part of speech tags for each word. Okay, so flies would be in the dictionary as either a noun or a verb, but it doesn't show up as an adverb, for example. So they have a little bit of information that way. And then they compare 5 different models. An EM model, which is just the standard HMM, trained with expectation maximization. So there's nothing Bayesian about it. And then there's VB, which is going to be an uncollapsed variational Bayesian HMM. So here they're not going to sum over the parameters of the HMM. They're actually going to maximize over them. And then they have algorithm 1 and 2 here for CVB, which is a collapsed variational Bayesian HMM. And in these settings, the collapsing part is just happening on these phi parameters, where just as we saw, sort of you could do collapse inference for LDA, you could also collapse these out. And then lastly, they also compare it to a collapsed Gibbs sampler. Okay, and one sort of cool part about this is just that when you actually look at the mean field updates and the collapsed Gibbs sampler updates, There's actually a lot of parallels between them. It's not worth kind of looking at the actual details of this, but basically in the mean field case, you're updating this distribution over the ZTs, and in the collapsed Gibbs sampler, you're sampling from a full conditional over the ZTs. Okay. And what they find is that like a couple things that aren't too surprising. So on the left here, we're looking at the number of iterations versus test perplexity. And so the uncollapsed variational maze is the blue one. It does the worst. And then algorithms 1 and 2 are the collapsed variational maze. And the collapsed Gibbs sampler is in purple. And so you can see that the Gibbs sampler is actually doing the best among these. The kind of key difference is just in runtime, where the collapsed Gibbs sampler is taking dramatically more runtime than any of the alternatives. And this algorithm 1 is actually doing significantly better in terms of speed than the alternatives. So why do they have all these different speed issues? So EM, which takes 28 minutes per iteration, is slow because of the log space computations that it needs to do. You need to do these computations in log space to avoid underflow. The uncollapsed VB is slow because it has these digamma computations. This digamma function is really expensive to compute. Algorithm 1 is actually the fastest, and then algorithm 2 is slow because it has these like dynamic changing parameters. And finally, collapsed Gibbs sampling is incredibly slow, much slower than any of the deterministic algorithms. You can also take this Bayesian HMM and apply it to other tasks. And there's this pair of papers, Foti et al. And Mamana and Chung in 2015, that looked at human chromatin segmentation, where they were actually trying to do unsupervised segmentation of the genome. And so they start with a huge data set of 250 million observations, and the metric that they're evaluating on is actually the sort of false discovery rate of predicting these known elements in the sequence. And so they compare these different models using Bayesian HMMs. And without going into any of the details, because I don't know the actual biology behind this task well enough to do it anyway, there's kind of some important machine learning takeaways. One is that the two models actually perform at similar levels for false discovery rate, but the variational inference model takes 1 hour, and the other one, the dynamic Bayesian network with standard EM, takes days to converge. So it's just dramatically slower. So for grammar induction, there's this great question, which is, can maximizing unsupervised marginal likelihood produce useful results, right? So we were just thinking about unsupervised part of speech tagging. So here, on our theme of babies, we could actually think about, how do babies learn? Well, babies are exposed to massive quantities of their native language, so say English, just by hearing all of these sentences. And somehow they're able to then piece together some complex representations of those sentences. And so grammar induction is asking the question, can a computer similarly learn the syntax of human language just by looking at examples? And so here, we're trying to recover this syntactic structure without any supervision. And for a given sentence, we've already seen this before, where you can have lots of different interpretations of the sentence depending on what your actual syntactic structure is for that sentence. And for the machine, they actually have to consider a bunch of semi-reasonable semantic interpretations and also ones that are completely semantically implausible. Okay. So here, the actual training data is just the sentences, and we're going to try to evaluate accuracy against gold standard parses. Okay. And so the question that we could ask is, does likelihood actually correlate with accuracy on, say, a task like this? And what we find is that, in fact, we do get this really strong correlation. So if you run the model many times over, the actual objective function that you're optimizing is non-convex, and so you get back a different log likelihood for each run of the model. So that's each point here. And for each model, you can evaluate not only likelihood on this horizontal axis, but also the accuracy against that gold reference set of trees. And so what we're seeing here is that, yeah, there is actually kind of this strong correlation between the actual downstream accuracy and log likelihood, even though the log likelihood is fully unsupervised. Okay, that said, if you pick a particular level of likelihood, say 19.4, there's still a huge range of accuracies, ranging from, say, the low 40s to the low 20s for that level of likelihood. Okay, so not surprisingly, people have looked at variational Bayesian models for grammar induction. I'm going to just kind of skip past this, but they do similar comparisons of EM and then different Bayesian models with different priors, like Dirichlet priors and log normal priors and so on. Okay, so before we talk about variational autoencoders, I just want to do a quick introduction to standard autoencoders, and then we'll move to VAEs, or variational autoencoders. So the idea of an autoencoder is that we want to train a deep network, and maybe we even have supervised data, but we want to, say, pick a better starting point for training, right? Because training is going to be some non-convex objective function, even if you're doing supervised training. And so we want to be able to come up with a way of initializing the parameters well. And so the idea of an autoencoder is to do what's called unsupervised pre-training, where we use unlabeled data and we work bottom up. So we're going to train hidden layer 1 and then fix its parameters, and then train hidden layer 2, then fix its parameters, all the way up to layer n. And then you could come back and do supervised fine-tuning using labeled data, and you could essentially refine the features by backpropagation so that they are well-tuned to the end task. Okay, so this is going to be idea number 3. I'll introduce idea 1 and 2 later so that we can compare them on a task. So the question for unsupervised pre-training is, what should we predict? If we're unsupervised, what else do we observe? Well, if we're unsupervised, we don't have this output, right? It's just not even there. So instead, we can try to use the input to predict itself, or a copy of itself. And so if you have a neural network where you have the input fed in here, and the output of the neural network is supposed to be a copy of the input, this is what we would call an autoencoder. Okay. And so the key idea is that we want to, so we set things up with an encoder and a decoder, where I guess I should call these aren't A's, they're Z's here. And so the hidden layer is a bunch of Z's, and we're saying that the encoder takes this input and gets us back a Z. And then the decoder takes the Z and gets us back a copy of the input X prime. And what we want to do is tune the parameters of the model so that Z gives us small reconstruction error, where we say that X prime is a reconstruction of the original input X, and our loss function is just, say, the L2 norm or something between the original X and X prime, where X prime is just what you get when you feed X into the encoder and then feed that into the decoder. Okay, so once you've set up your loss function this way, then you can just train using backprop, because this is just a differentiable loss function like any other. So why would this work at all? Any thoughts?
why are we actually going to learn something interesting?
We're constraining the number of hidden layers to be smaller.
Yeah, usually. So if we say that the hidden units, there's going to be a small number of those. Say the input is actually an image, like a 100 by 100 pixel image. Okay, so there's 1,000,000 pixels in your input, and that means your final layer, the reconstruction layer, is also 1,000,000 pixels. But the hidden layer, let's say, is just taking it all the way down to just two hidden units or something. So we're going to try to compress all of this information about the image down into 2 hidden units and then reconstruct it with the decoder. Okay, so the idea when you apply this to a deep network is that you can work bottom up, right? So you can basically train hidden layer 1, and then you fix its parameters, and then you keep those bottom ones fixed, and then you can train hidden layer 2 and then fix those parameters, and train hidden layer 3 and fix those parameters, and all the way up. And then you can do supervised fine tuning and backprop all the way back through. Okay. So this is now honestly kind of an antiquated idea in some sense. It's still a fundamental idea that we've come up with like better tricks for how to make this work really well. And in fact, if you're training a deep net, this isn't necessarily necessary, but it still gives this lovely picture that we can see an autoencoder in action, where it first showed up in 2006, where we're going to compare 3 ideas. One is supervised fine-tuning only. The second is supervised layer-wise pre-training, where we train the first layer to predict Y, and then the second layer to predict Y, and then the third layer to predict Y, and then finally the last layer to predict Y. And then idea 3 is going to be this unsupervised autoencoder to initialize supervised fine-tuning. Okay, so what you can see here is if you just have a shallow net, this is on MNIST digit classification, so this is sort of a now classic problem where we're trying to predict which handwritten digit an image is showing. And the idea 1, which is just a deep net with no pre-training, actually does worse than a shallow net. And so the second idea is, okay, well, what if you do supervised pre-training? So this is error, remember, lower is better. And the deep net with supervised pre-training, it does better than no pre-training, but it's still worse than the shallow network. And then the idea of unsupervised pre-training actually succeeds in getting something that's better than the shallow net. So this was revolutionary in 2006, but we've come a long way since then. And in particular, one of the methods that's really sort of garnered a lot of attention is that of variational autoencoders. And the whole idea of a variational,
Is there any reason why we're doing it layer-wise instead of just having one giant autoencoder?
Oh, you absolutely can. I'm just showing you how it was done in its first instantiation in 2006. So if you were doing it today, I would actually recommend doing it all at once rather than the layer-wise pre-training. We kind of figured out afterwards that, we learned a couple things since 2006. One is that you can actually get the deep net with no pre-training to beat the shallow net if you just throw it on enough GPUs that you train it for like a much, much longer time. And then the deep net actually can succeed even without autoencoder pre-training. The other thing is that you don't necessarily need to do this layer-wise pre-training. You can use an autoencoder like objective function and just train the whole thing all at once. And so the variational autoencoder, that's exactly what we're going to do. We're going to train the whole thing all at once. We're not going to do anything layer-wise. Yeah, great question. Okay, so this is the picture. The reason that I highlight this though is just this gives us this picture of an encoder which takes your input, maps it down to some low dimensional representation, and then the decoder which takes that low dimensional representation and maps it back up. Okay, so the variational autoencoder is going to do that, but in a probabilistic setting. And so, so let's start by actually thinking about the variational autoencoder. we'll begin by thinking about it as sort of the way that a deep learning person might talk about it. So variational autoencoders, or VAE. Okay, so the neural net perspective here is that we're going to say we have two components. We have an encoder and we have a decoder. And the encoder is going to be a distribution, q theta, or q parameterized by theta, of z given x. Okay, and if we were to draw sort of computationally how this encoder works, you would say, okay, at the bottom, we feed in, say, some image x. And then there's some function which we'll call encoder underscore neural network. And this is a function parameterized by theta of x. And the output of the encoder, this is where things get interesting, is not directly it's not directly z. Instead, the output of the encoder are some other parameters, let's call them mu and sigma. And those parameters are going to get fed into a Gaussian distribution, parameterized by, so we'll say this is a Gaussian over parameterized by mu and sigma. And, oh, I see what I'm sort of hesitating on here. So we want to make clear that this is a Gaussian distribution over output z given the parameters mu and sigma. And so the output of a Gaussian is actually a sample z. Okay, so what do we have here? We have, say, our input, which is something like an image or other input data. And then here, this is a deterministic function of neural net parameters, theta, and our input x. And lastly, up here, z is sort of our latent variable that we'll come back to. And I guess the other detail is that this is a stochastic function of mu and sigma. Right? So the Gaussian is actually where we actually get the fact that this is a distribution over z's, right? It's not a deterministic function from x to z. The deterministic part goes from x to mu and sigma. But then from there, we actually have a Gaussian distribution parameterized by those. Okay, so then the decoder is going to be some p parameterized by phi of x given z. Okay. And here, we say that, oh, sorry, this is going to be a decoder that is a joint distribution over x and z. Oh no, let me actually do it this way. So we're going to think about p of x given z, but we need to think about it in the context of a joint distribution. So momentarily, we're going to be thinking about a joint distribution P of x and z, where we have two terms, P of x given z and P of z. Right? So we have like a sort of a likelihood and a prior type distribution going. And so here we're just concerned with that P of x given z. Okay, so what does this look like if we draw it out computationally? Well, this is going to take in a z, and it's then going to feed that z into a decoder neural net, which is parameterized by phi, and a function of z, and its output is another set of parameters. Let's call them mu prime and sigma prime. And these parameters are going to be fed directly into another multivariate Gaussian, where now this Gaussian has parameters mu prime and sigma prime, and it gives us back not a distribution over z's, but a distribution over
x's, or reconstructed x's.
Okay. So here, we could say, well, again, down here we have this latent variable, z, as before, and then this decoder is a deterministic function of phi and z, and then the Gaussian is stochastic, and this x is our sort of reconstruction of the image, or something like it. So this is sort of the two pieces that we're working with here, an encoder and a decoder. And if we were to just say, okay, this is just going to be a standard, good old-fashioned neural network, okay, then what we would do is we would just say, okay, let's write down a loss function. And that loss function is going to be some example-specific thing, right? So we're going to say that our true loss, L, is equal to a sum from I equals 1 to n of these Li functions. So maybe L is a function of our parameters theta and phi, and Li is just
Sort of an example-specific, an example-specific loss function.
So the question is, what should we write down as our example-specific loss function? Okay. So we're going to write it down first,
And then we're going to think about why it actually makes sense.
from a variational perspective. So the loss function is going to be an expectation under q of z given xi of a log of the probability under phi. So this is this is for q parameterized by theta, and p parameterized by phi of xi given z, plus a KL divergence between q theta of z given xi and that prior term that I mentioned before, p of z. Oops, it's all the way over here.
All right. So if you squint at this thing, you should be thinking to yourself, huh, I was expecting something that looked exactly like the elbow. But this doesn't look exactly like the elbow. And so let's try to figure out why that's the case.
Okay. So to do that, we want to take another look at this variational autoencoder, but this time sort of from a graphical models perspective. All right. So the model, in this case, is just going to be p of x and z, which decomposes as p of x given z times p of z. Okay, and so far, this should feel completely uninteresting. So the p of x given z is the part that's parameterized by theta. And so if we were to draw an actual graphical model picture for this, we would have one zi for each example and one xi for each example. This is going to be a plate diagram. And if we had n training examples, there would be n of them. And we also have parameters out here, theta. And the thing we observe are the actual xi's. All right, so thus far, all we've done is written a really, really boring looking model from a graphical models perspective, right? So why is this going to be interesting? Well, our goal is going to be to estimate the posterior, p of z given x, okay, which is a function of theta as well. And we would say that that is equal to p theta of x given z times p of z divided by p theta of x, right? And here, the key point is that this is going to be intractable. And the question is, why is this going to be intractable? So what is it about what we've done so far that makes you feel like estimating p theta of x should be intractable? Because honestly, if you just look at it like from a graphical models perspective, it doesn't look like estimating p of x should be all that hard. Zoom out a little here. Any thoughts on why estimation of p of x might be difficult? Isn't the distribution over x just a Gaussian? According to our definition of the decoder? Just a plain old Gaussian, right? I know how to do posterior inference with Gaussians, plain old Gaussians. Is this a plain old Gaussian? Is there something more complicated?
Because it's very high dimension.
Exactly. So it's not just high dimensional, it's also conditioning on something high dimensional. So suppose z was actually some low dimensional thing. Say z was just a single real number. The way that we generate x from z is not just to say that x is just a simple drop of a Gaussian. We first have to pass through some big complicated neural network, right? What we're looking at here in this decoder neural network, this thing might actually be something like a many layers deep
like say this is Z1, I mean, Z really could just be a single value, or maybe it's like two values, Z1 and Z2. But then maybe these values are fed into some complex, many layers deep neural network, which after a while outputs something like a mu1 and a mu2, and then sigma 1, 1, sigma 1, 2, all the way down to, say, sigma 2, 2.
So the point is that this decoder is not just a simple Gaussian. It actually has some complex neural network built into the definition of how it is that we sample X.
Okay, so back to the graphical models perspective. What can we do about this? Well,
If it's going to be intractable,
so the answer to our why question here is because of the decoder neural network, making P of X given Z a complex distribution. Okay. So what we're going to do then is we're going to say, well, come up with a variational approximation. And that variational approximation will just be some q lambda of Z given X. So these are our variational parameters, lambda. And this is our variational distribution. Okay. And so why are we talking about this lambda here? Well, the lambda in our variational setup here, if we come back up here, the lambda in our variational setup is going to correspond to the mu and sigma in our encoder.
so what you can do is you can think of this as, from a graphical models perspective, mu and sigma are this just deterministic function of X. And the distribution that we care about
Is actually just sort of this part, right? Which is really like a q lambda of Z given X. Okay. So now, if we write down just sort of the standard elbow, so this will be version 1, 3 elbows. Or no, I guess we'll just do 2. Two objective functions. Okay, so the first would just be, if we wrote down elbow of lambda here, then what we would have is an expectation under q lambda of the log, and this is of Z given X, of the log of P of X and Z. And then we'd subtract off expectation under q lambda Z given X of the log of q lambda of Z given X.
So the first trick that we can play
is we can say here that in this first definition, we're setting this up where z is equal to all the zi's from 1 up to n, and x is equal to all the xi's from 1 up to n. Right? So that's like the whole collection of all the zi's and the xi's in our graphical models. And so we can rewrite this elbow now as an example specific elbow, say elbow of I of lambda. And we get this simplification that occurs because of how we've parameterized things. So we have the same expectation of q lambda of over zi, or sorry, over, say, z given xi. And actually, let me just write this as a sort of vector x, vector z, vector x, vector z. And that's what we're calling the full collection of them. So down here, we're just working with the distribution over a single pair of a single z and a single xi. Okay. And so here we have an expectation over the log of the probability of xi conditioned on that z minus a KL divergence of q lambda of z given xi and p of z. And so the fact that we can get this decomposition back is because of the shared dependence on theta across all of the examples. And the fact that pz then does not depend on theta. So now, this is just sort of via some algebra, we recover the sort of neural net perspective loss function. And so if we go back and think about that neural net perspective loss function, we could say that really what's going on in the neural net version of the loss is that we kind of have two terms. So this is the neural net loss at the top there. The first term is basically a reconstruction loss. This loss is saying, under our approximating distribution Q, how well did we reconstruct the true xi? And then the KL divergence is kind of like a regularizer that says Q theta should be close to whatever P of z was. Okay, so now we can, we're almost back to the neural net version, except that this is still a function of lambda. Lambda is a function of x through some neural network. Namely, if we think about this thing again, so recall here that our encoder is essentially saying lambda is equal to, this this mu and sigma, which is the output of some encoder neural network parameterized by theta as a function of x. And then we have that we get this distribution q theta of z over z given x and lambda. Oops. Okay, so this is our encoder distribution, now as a function of the actual neural net parameters theta. And the decoder is really this joint distribution that we're trying to approximate, which is p of x and z, which is some complicated neural net and some simple prior. So namely, the simple prior might be something like n of 0 and I. Like this is really just going to be a standard unit Gaussian. And then this is going to be a multivariate Gaussian where mu prime and sigma prime were equal to some decoder neural network parameterized by phi of z. All right, so finally then, if we rewrite this example-specific elbow, but now in terms of the neural net parameters rather than the lambda parameter, what we get back is an elbow sub I of theta and phi as this expectation, but now under q theta of z given xi of the log probability of xi, given zi, given z, the thing over which we're taking the expectation, minus this KL of not q lambda, but q theta of z given xi and pz. So here, this is just sort of rewritten in terms of theta and phi instead of lambda. And the whole reason that we do that is that lambda is a deterministic, really a neural net function of theta. Okay. So what the variational autoencoder is accomplishing is it's just setting up for us this incredibly complex distribution, right? You know, on the surface, it feels like, oh yeah, we're just sampling x from a Gaussian, we're sampling z from a Gaussian. Simple. But the incredible complexity comes in because there are these deterministic encoder and decoder neural nets that give rise to the actual parameters of those Gaussians. And so if we want to do posterior inference in a model like this one, then we can't at all rely on sort of the simplicity of the Gaussian. And instead, we can turn to variational inference to actually accomplish the problem that we set out to solve. And so training here is actually simple. It's just standard variational EM. Where we're trying to maximize elbow of theta and phi. And so just as in variational EM, we just go back and forth between optimizing over theta and optimizing over phi. So the parameters of the encoder then optimize the parameters of the decoder, and back and forth. Okay. So there's an important detail here that probably was not obvious, and that is about backpropagation. So here, this figure, all it's done is it's taken the encoder picture that we drew and the decoder picture and it put them together, right? So here's the encoder picture that goes from X to Z. That's the encoder that we just drew. And then here's the decoder picture that goes from Z back to, this f of Z is just X, or a reconstruction, X tilde. And the problem with this picture is that there are stochastic parts of this picture. Namely, we're sampling Z from this multivariate Gaussian. And we can't backpropagate through sampling. So what do? Instead, what we can do is we can say, we're just going to sample some epsilon from the unit Gaussian. And then we're going to take that sample epsilon and multiply it by the covariance matrix and add the mean. And that will give us back the same thing as a sample directly from that Gaussian. And the key here is just that no longer is the actual sampling in the critical path if we want to backpropagate to the parameters of the encoder. Yeah.
So in the diagram, it seems like you don't sample from decoder, but I think in the notes you actually said we sample from a Gaussian from the length variables.
Oh.
Maybe you don't know.
Yeah, so what we're doing here is not, so what we're trying to set up here is just a training objective. So in principle, you could sample from this thing, right? And the way that we were thinking about this is that, you know, if you were to actually get a Z from the encoder, that is a sample from the Gaussian.
Right.
But then in the decoder, we don't typically sample an X. It's kind of like think about what you're doing when you're training any neural net with a softmax layer at the very end. If you know what the true label, say you're doing image classification, you get a softmax over the labels. And what you do is you want to maximize the likelihood of the true label.
Right.
So here, rather than actually drawing a sample X, or a sample X tilde, we're just going to maximize the likelihood of the true X that we wanted to reconstruct.
So the decoder then will predict X tilde, not mu prime or epsilon prime, or sigma prime.
So the point is that the decoder is just giving us a distribution over P of X given Z, and we're going to tune the parameters phi to maximize to maximize the likelihood of the observed X's.
Okay. But what about the mu's and the sigmas?
The mu prime and sigma prime?
Right.
Yeah, so those are the actual parameters that we'll tune.
Okay.
And so what we're doing is, so mapping back to what we had been thinking about with variational EM, we have the parameters of the approximating distribution, the parameters of Q, that's theta. And then we have the parameters of the true distribution, P, that's phi. And just as in, if we were just doing variational inference, it would be like saying, we already know what the parameters phi are. Those are fixed. And we're just trying to infer some approximating distribution, Q of Z given X, that best approximates it. So that would be pure variational inference. But here we're doing variational EM, which means we're simultaneously learning both the parameters theta and the parameters phi of the true distribution.
But you're taking the MLE, right? So that means it'll just be mu. Wouldn't the MLE of Gaussians be mu?
The MLE of the which Gaussian? Because there's two.
The bottom, decoder Gaussian. If you're taking the most likely, it would just be mu.
Oh, sure. You mean mu prime here?
Yeah, mu prime.
Yes. So mu prime, the most likely thing would be that mu prime is exactly whatever x was, right?
So you don't ever use sigma.
Except that, oh, I see what you're saying. Sorry, sigma prime here, you're saying, oh, you're just talking about the covariance, not matters.
Yeah.
Yes, okay, yes. I think you're right.
It's just
so-
in training because you need sigma to calculate the log PDF.
Yeah, so you can't compute the likelihood without it. So it does actually affect likelihood of x though. So there is a sigma that could make x more or less likely, depending on the current value of mu. So mu, we're not going to do we're not going to do exact like closed form optimization here. We're going to take a gradient step. And so at any given moment, we might, like the maximum likelihood estimate of mu, you could say is going to be exactly x for the single current training example. But for a given sigma, the best mu might actually, like you're going to take a step in the direction of the gradient.
Okay, so so the point of the reparameterization trick
Is that we can just take that stochasticity out of the computation graph and back propagate all the way through this thing to get back a distribution that we actually wanted.
and so the sort of the thing that I don't have time to go through is that
We can actually take this a step further, and we can look at generative adversarial nets.
and VAEs, and we can put the two side by side by actually thinking of GANs, which have this
Very, very different look to them, right? If you think about GANs, if you've seen them before, they're kind of this setting where you have a generator and a discriminator, and you're trying to have them
sort of pitted against each other. And you can reformulate GANs also in a variational EM format, such that when you put
GANs and variational autoencoders side by side.
you realize that, in fact, both of these are sort of minimizing a KL divergence.
But the VAE is minimizing a KLQP, and the GAN is minimizing a KLPQ.
And so,
The idea is that you can actually recast what sort of the neural net community had thought of as these two totally disparate methods as being two sides of the same coin. And you can then also think about, what might live as sort of things in between the two, or like combinations of those two learning objectives.
okay. So the part that I definitely won't cover today, that we'll leave off at, is there's lots more to say about deep generative models. And so you can take a lot of the
things that were being done sort of in the early parts of deep learning, and you can actually recast them, those neural networks, as graphical models.
And in fact, a lot of the sort of methods that we had thought about take things like, oops, let's just jump to this one last slide.
So you can take these things like deep belief networks and deep Boltzmann machines, and you can revisit them with a graphical models perspective and see that like a deep belief network is actually this hybrid of a directed and undirected graphical model, and a deep Boltzmann machine is this purely undirected graphical model. And there's other variants like restricted Boltzmann machines. And the actual methods that we use to actually work with these things actually look back at the sampling methods that we had talked about, things like Gibbs sampling. So there's lots of these really interesting and rich connections that exist all the way from sort of the graphical models community to the deep learning community. And I think gradually these two are starting to kind of bridge the gap and see a lot of these connections being made. So anyway, this is where I think a great place to leave off, just to say that what we've done here is sort of given you the foundational materials that allow you to kind of continue your learning and go out
and better understand what's going on broadly in the field, whether it be by sort of continued learning in other courses, if you're sticking around CMU, or continued reading on your own as you are kind of going off and sort of changing the world in industry or what have you. Anyway, so I had a great semester with you all. We'll see you on Thursday evening for the final exam. So catch you then.